Прежде чем мы представимся, на самом деле очень хочется задать
Before we will introduce ourselves, I would like to ask the favorite question that we have. Please lift your hands if you know something about the company 1440.
Обычно намного меньше людей, но тем не менее...
Usually much less people, but nevertheless, half of you don't know about us. So we would like to tell you a couple of words about our company so that you would understand that we are not speaking just about some outer space ships. 1440 is the largest commercial Russian company which is involved in outer space. Airspace company. We are making low orbital group of satellites consisting out of 200 or even more satellites that will provide services of wide band access to the internet. Why we have decided to speak about this topic, and not many people speak about it. However, we think that we should speak about it, and we have to work on it. Why? Because we are speaking about this because one of the main reasons we want our company to be known by many people, and we want to have more talented guys coming to work for us. And second of all, right now, satellite industry is growing, which is very nice, and space is accessible even to the children, as strange as it may seem. And possibly some of you, maybe some of you who will watch our presentation will become the security specialists who will be involved in security of space systems. And if this security person will come and will start using exclusively those tools and methodologies which everybody hears about, like PPO, DevSecOps, then unfortunately it's not going to be good for everybody. They will not achieve success. So let's begin diving in the topic. It's the wrong presentation, Misha. We are going to tell you in more detail. In the company, we have launched 2 missions. Mission is a project, and we're going to tell you about it in detail. Currently, we have 6 satellites on the orbit, and on these satellites, we have tested all the technologies, and we're planning to launch commercial satellites very soon. So let's dive in. What is the space system? It is obvious. Satellite system, space system, is a system which flies in the outer space. It has the control system, which is a land-based infrastructure which provides communication with the space constellation of satellites, and management. There are operators which control these satellite systems. Today we're going to tell you about satellites, and if you will speak about satellites, then satellite as a rule consists of 2 main functional subsystems, let's say. This is management control subsystem, which allows satellite to live on the orbit, and the useful load, something that gives usefulness from the satellite. Well, the payload can be some visual observations, payload can be geopositioning, anything can be a payload. Everything that you know about space systems, this is about the payload. So in our presentation, we're going to use this spaceship, a typical one, and we will put all these payloads that we're going to speak about, and we should follow the terminology. The first word, which is very romantic, is a mission. Mission for us in the space, it's a project or a program of launching satellite constellation to the space. It's a mission. We also are going to use the cyber-physical system, which Misha was speaking about. What is cyber-physical system? It's something physical which is controlled by the software. It can be a satellite, a car, robot, for example, anything that can be controlled to the software. And most likely you all heard about abbreviation
составляющая космических систем.
ATC, it's also a very important part of the space systems.
Понять,
So
что
let's
сейчас вообще происходит
move
с космическими
to the past
системами.
to understand what is happening with space
Посмотрим на
systems
фреймворк, который написал НАСА еще более 20
and look
лет
at the
назад,
framework that was written more than 20 years ago,
Fly System.
Core Fly System framework.
Сами НАСА говорят о том, что на этом
NASA tells us that on this framework they've been writing more than 40 missions by NASA
миссий по всему миру.
and more than 90% of missions all over the world. What is the most interesting in this framework is that it doesn't have security at all. What was the consequence? That there were attacks, and we are being surprised why so late. The first research of this attack happened in the year 2023. CubeSats have been attacked. What is a CubeSat? At the bottom left corner, the super small spacecraft. It's called CubeSat. It's in the hand of a person. There are different, there are stacks of them, but they are very small. Some student missions, and they take complete sections in order to revitalize it and receive some usefulness from it. So very often this CoreFly framework or system is used to make such a robot CubeSat. And the first research happened about these devices. This year there was research number 2, and we see some development in this area because honestly the equipment that is needed to get connected to this equipment is not expensive. Open source is available. You should understand where you should shoot with your antenna, and then you get connected to the satellite. So if you are speaking about serious things, then you should mention a recent attack in 2022 against Viasat. The attack was destruction of the land infrastructure. They are not speaking about it, but honestly speaking, we can read that most possibly their spaceships also have suffered.
Spacecraft have also suffered. What we are seeing from our satellites, you can see this image from our satellites. These are attacks on GPS and geopositioning systems. You can see the coverage at the moment on a global scale. You understand why these attacks are taking place. If you want to dive deeper on these attacks, we're not going to spend too much time on that because we have different topics. I'm recommending you this report. It's a great report to read. So, what would be the target for an attacker in terms of space system? At least, let's go from the simplest thing. You can break a spacecraft and make it into a space trash. Then they do the interceptions of the space data. Even the amateurs do this from the meteor, satellites. All kind of guys, all kind of amateurs are just connecting data, visual data that this thing transmits. And the other thing would be even the capture of the spacecraft under your command and to use it for your purposes, because the spacecraft is very, very costly, and it also can be very beneficial in terms of what it provides. Let's go deeper into story, into history, and think about the first ever Sputnik, the satellite of the Earth orbiter. Why it was not possible to attack the first orbiter? Actually, it also had some good payload. Can anybody give me the payloads, information about the payload? Why it was not possible to attack it? Because it did not have any software. And the first ever Sputniks or satellites, they were composed of the physical analog systems, and they had some electronic management but no software. Whereas main satellites are quite more complex, and you have the hardware and software things, and This enables to attack this satellite. And the electronic architecture of a spacecraft is much more complex than on the previous picture, because as you can see, there are a lot of electronic components, and speaking about the number, then the number of such electronic components could be dozens. And the architecture of a spacecraft is very, very close to the evolution of the automotive systems evolutions. Like we have less hardware stuff and moving functional part into software, because software is easier to write, easier to change, and the cycle development of software is much shorter than developing hardware systems. This is why it looks like it's going to be 1 to 3 supercomputers, and this is just a regular stack like hypervisors, virtualization, containerization, Kubernetes could be there. By the way, it flies in CubeSats, in a smaller satellites, and also functional software on top of it. How do you manage this, let's say, satellite? Since a satellite is orbiting Earth for quite a long time, it's beyond the visibility. I mean, the flight control center cannot see it, cannot manage it, or guide it. That's why it has a flight task preloaded into it. It tells the satellite, depending on the time or location or other events, it prescribes it to do certain things. And if you do analogy with what a satellite is all about, then if some of you know familiar with automotive systems, basically a satellite is like a car, but autonomous car, which flies in orbit of the Earth. This is the car by Elon Musk. What are additional challenges can be met by those who are developing this type of systems? First of all, after a Sputnik or satellite has been launched, if something broke down, what can you do, right? You cannot repair it unless it's a software. It can be fixed. Next, in terms of security, they are flying over territories we cannot control, and from these territories, some people may try to attack satellite, and satellite is flying in quite aggressive environment, which potentially can impact electronic components and cause different types of malfunctions. So if we will imagine that satellite is flying, it is not manageable for some time. Then in terms of the safety architecture, we have to develop this like a cyber sustainable system. It should be able to defend itself. It should be able to identify a threat, to respond to a threat, and to recuperate every threat if there was like a certain compromising event. Yeah, and if a company decided to install a security component into a space system, they attract a security architect. And if this architect comes in at the stage of software development, then you can say, hey, good job, you guys won. Why? Let's give an example. Because as soon as an architect, studies context, begin to analyze the architecture, then one of the elements they may want to add to that would be firewall at the entrance of the onboard system. This firewall may require very serious overhaul of the hardware and changing the network architecture and so on. And this kind of overhauls may cost may give you like a 1 year, but the rocket is already in space. Another possible element of defense could be the communication channel defense. And here you can find that some algorithms of encryption are not supported. You cannot switch, you have underutilization of resources, and overhaul may roll you back by 6 months at least. Now, what do you do? Because the safety and security should be implemented, embedded on the stage of design of the system. And we are going to illustrate what information security officer has to do at each stage of developing this product. Giving you a network spice, in the A-Spice, we've taken six main groups of processes, and also I want to say that these processes can be clustered into blocks. First of all, is of course design of the system, and the second block would be the development of the software. At stage 1, we do requirements, we collect requirements, and here we want to focus on the final stage. And you can see the first several steps would be usually identify the risks and the models of attackers. But since our target audience are architects, let's talk about requirements. When it comes to requirements, there is nothing like super unique, because the information security officer is setting up the same requirements for the access control, data protection, and at this stage they have to highlight what security systems have to be embedded with the product. Again, at this stage, there is nothing unique in the composition of control. This uniqueness will show up later. We all have to be able to implement these control systems seamlessly into a spacecraft. Like we said before, when it comes to call, we need to develop a cyber-physical system, a cyber-sustainable system, cyber-proof, which would have the following capacities, like being able to protect itself. Like Vitaly said, now, when it comes to the control requirements of what has to be embedded in a spacecraft, spacecraft right here is not something unique. All controls are exactly the same as you and I are seeing, like in a corporate network. However, embedding them into a spacecraft is quite a feat for engineers, and a special attention that we want to draw. Speaking of these control measures, that you must not forget about keys management. Many people forget about that, but the keys management is not only about organizational component, but possibly it's also going to impact hardware component. But hardware can roll us back 6 months, back in time, and even more. And speaking about security tools, the security tools have been identified in documents of different regulators who are responsible for space exploration. And we recommend, first of all, look at the documents of the CCS-DS. There are main security tools and very good descriptions of how to do keys management. There are some different keys of different payloads, and how you can use separation of keys, and things like that. We are not going to elaborate on that, because you can read those measures, and we are going to move on for those elements which you may not find in space systems. Either they're non-existent, but still there are some other frameworks which may be helpful. Third-party frameworks. And the first thing we'd like to draw your attention to, and basically to show it, of how to protect command and control. The command and control is about loading flight assignments. In addition to flight assignments, you can also, configuration can come in, and then new software upgrades, come in. You can do this, you can do the upgrades. And all of this looks just like files. They're not commands, they are files. And if these are files, then we recommend pay attention to such a framework as Optane. Optane, which describes safe updates for cyber physical systems. It has been developed for cars, for automobiles. It's based on a different framework. I think you know it. It's a framework, TÜV data framework, which is like the common for safe upgrades. And this framework Optane. It specifies TÜV by for the cyber physical systems. In this kind of systems, oftentimes control blocks, they are different control units. There are some smart control units and very limited control units. If you will try to build requirements for them to double check on the signature, then the limited control unit cannot do that. And this framework actually describing all of these details. How can you do it in the right way to make it safe and take into account all those limitations? Okay, that's it for defense, and let's talk about detection. Detect. Before speaking about detect and just a little bit of baseline things about the space systems. Space systems has a number of functions which may become unsustainable and result in this kind of unauthorized event for a company. The reason of moving in a stable event could be some kind of malfunction, and this is where the most interesting things happens. We have a goal how to separate just the malfunctions from intentional tampering by a person, cyber attack. To answer these questions, we are moving on to the next stage, analyzing requirements. And the first thing we need to do is basically, if you've ever been involved in cybersecurity for complex systems, you may have faced this situation when a lot of requirements are rolled back, and developers and business, they're asking, okay, if we do all of that, does it mean that we'll fly like in 50 years? We cannot wait that long. You have to give us priorities. What is really important to do it here and now? And as you remember before, we have to do the seamless controls that have to be built. And the information security officer can say that, yes, we can specify these requirements, but give us design. And developers saying, give us requirements and then we'll give you design. So it's like a catch-22, right? And sort of like a deadlock, dead end. But actually there's a way out of this situation. We can be helped by the threats modeling, top-down analysis. But to do it, we need to rebuild context of the system. Like Andrei has mentioned, the structure of the spacecraft is like a predefined, and all the main elements or all the blocks can be depicted or can be shown as a context, adding business expectations, and this will help us to start our analysis via modeling top-down. What does it mean? We are using this arrangement, this scheme. We can do the brainstorm, a bunch of analysts involving also the people in domain, the space systems engineers, to understand what may go wrong, what may be the problem. Let's see. Just to give an example, in the most adverse scenario, this would be like lost profit. What could be the reason of this event? For example, the service degradation. And the service degradation, like what can lead to service degradation, to this kind of consequence? For example, losing communication, losing the spacecraft, and then you can branch out to different consequences. We can ask, like, what may result in malfunction of a spacecraft? For example, malfunction in one of the systems. The most interesting part right here is that as of right now, we haven't spoken about the safety security. We're speaking about the negative consequences and some kind of breaking downs and malfunctions. But security begins at the next stage. Why am I emphasizing that it comes a bit later, security-wise? Because this exercise of top-down modeling, this can be done by the architects, and InfoSec is stepping in at this stage. When we ask ourselves, can this malfunction be caused by a cyber attack? And then we sort of like, looking downward, we can identify a threat, like what can lead to this malfunction, what kind of a threat. And right here we specify our controls. As you can see, each of the controls, they immediately showing us the most negative, the most dangerous consequences. It's important. This kind of control of the business becomes much more visual. And we can say from experience that engineers, they are much more willing to be a part of this kind of exercises, modeling, because again, everything is very, very transparent. Also, I have to mention that since we know about potential threats, we can identify DPS sensors. Andre is going to give you a bit more details, and we are saying that the source of this could be threat modeling. And also, having this kind of updated list of requirements attached to the context, we specify our requirements. At the next stage, we have a design, and right here we have to already count in firewalls and other systems and other control measures. At this stage, when we already have design available, we can update our top-down threat model, and the quality system is working, because some elements and some units could be omitted by us. We may not see them, but after this detailed analysis, we are closing this gap. There is one problem, maybe even big problem, So when we do the top-down modeling, it all depends on experience of those analysts, security analysts and experts from the domain. And this expert level is, is a risk of a cognitive trap. There is a lot of human factor. And to be able to close this gap, we absolutely have to do a formal analysis, like a top-down formal analysis. And right here, we can see the stride stack. When we have a design, we can formally model threats and double-check on them. And should we identify any problems, we can specify them, we can deal with them. And only then, we have 4 next stages: development of software. I think it makes sense. It's pretty obvious. We have to do everything according to the standards. Going back to the architecture, we have analyzed all the malfunctions. We've identified locations where these malfunctions could be caused by the human factor and human error. And we've identified those logical sensors what we need to install across a spacecraft. And in our example, I've set them up like that, and you can see that I've set them up on the firewall, connection module, and also we have sensors which are responsible for the onboard system, basically for analyzing functional capabilities and functional anomalies, so to say. And also this could be monitoring the situation. We've made these sensors and we're getting some security events. What do we do with this? It is obvious that we have to react to that. It's another engineering feat which has to be done. Usually, responding in the classic systems is done with SIEM. We're taking an event, upload it into SIEM, correlate, identify some events and incidents which we have to respond to, and then give a command to this management system to give a command, to the spacecraft. But the problem is that spacecraft is not always connected in connection. That's why we do not always see it. We cannot always give it a certain command. That's why we have to pre-build SIEM into a spacecraft, and in this case we take those events right from the spacecraft. It has to have certain rules to analyze correlations and reacting, and SIEM in this case is going to issue recommendations into telemetry So what could be done with a spacecraft? And telemetry is responsible for viability, survivability of the spacecraft. Like, it cannot receive all the commands from the SIM. It's going to look at the overall state of the spacecraft. Would that be safe to do this command or not? And how can we develop this kind of stack? It's quite interesting specs from the world of transportation, like automotive things. This would be like a DPS, AUTOSAR DPS, IDPS, intrusion detection prevention system. It's all like together, and with the cars we have the same problem. Oftentimes it may not be connected, and it should be able to react to cyber attacks. And right here in these specs you can find everything. You can find sensors and analysis modules and response modules. There's even notion of safe memory. There is a notion of reporting when this analyzer kind of responds, and it also to notifies SOC and CM on what's going on. On this spacecraft specimen, I've installed all of that, and as you can see that the response module highlighted by red, I put it down not only in the main calculation module, responsible for logic, but also in COM module and also in firewall. Because it's not only the spacecraft can respond, but also separate electronic blocks, meaning that all in all, level of response could be different. They may begin with the hardware, like COM, communication hardware, that could be brute force, and it has to slow down the answers and block the source and block the whole territories if we're flying over some unfriendly territory. Then spacecraft can react by receiving information from sensors. It can make a decision that certain key module has been compromised, and we have to move on to some kind of like a safe state, for example, safe of being compromised. In these states, even physically, it can disconnect parts of the equipment to contain the attack in the spacecraft, and then to wait for a command from the flight control center and try to respond it into normal state. We can also react on the level of the whole system, like in our case. This spacecraft could be several hundreds, and the infrastructure could be like thousands of on the Earth stations, land stations. If one of the elements will be compromised, this on the land, on the Earth, this could be even a physical compromise, and when somebody can just destroy or break down, like here in Taiga in the forest, we will not be able to respond. So we have to have an opportunity, each of these elements to mark as the one that is compromised and take it out of operation. Next, let's move to yet another difficult engineering challenge. Okay, let's say we identified, detected, responded, and the satellite moved in the states of being compromised and switched off part of the hardware. How do we recover? And the thing here is, like, what do we trust? What do we trust in a spacecraft? And what kind of components? It's another engineering challenge we have to think about. And here we are using this kind of approaches like ARM company, IRM, with a trusted execution environment. But it was done for microprocessing, but still as an approach, it's quite interesting in terms of logic. I mean, you're breaking apart, you're separating this whole system by a couple of domains. There could be more domains, a trusted one and non-trusted one. And if we're speaking about recovery should be happening from a trusted domain, because we trust it. Why do we trust it? Because it has to be, super productive. And in addition to splitting up the craft into domains, we have to remember that the control units also should be enabling us to do the recovery. This will be like A/B sections or any other approaches which will enable you to restore the block, because if this block has been compromised, so that, bootloaders has been, erased, that could be just a brick, could be turned into a brick. This cannot be allowed to happen. So we gotta think about this. All of these are engineering issues, engineering challenges. So we've made like a very structured information about how you can protect spacecraft and space systems. There are a lot of frameworks and standards existing for that. We are showing them on the slide for you to be able to study them offline. Summing up, the goals of security is building autonomous, sustainable space system, and this safety should be able to take part in on the design of the system. And speaking of controllers, they're just regular controllers, and they are quite standards. But the point is that there will be the very unique system. Threat modeling is yet a very important aspect. It's not just a formality. Not just a formality. It will help you to identify the most critical part of your control system. Each of these elements, like a top-down, and they're usually kind of add to one another, complement one another, and the level should be so you do not kill the spacecraft. But again, we're making this spacecraft according to the state standards. Thank you. Any questions, please? Check. Yeah, please go ahead. Yes. Oh, just a second. We need some mic runners to give you the mics. Yep.
Добрый день.
Hi, my name is Sergey. I'm independent researcher. Very, very interesting presentation. Thank you indeed. And when you first began to, begin to speak, I was thinking about questions. You've answered like 3 of my questions. I have 2 questions, if I may. Number 1, you said that if a Sputnik or satellites who is out there, or maybe it's not a Sputnik, like something which is flying into deep space, as a spacecraft. If the software is going to break down, we're doing the patch, we're uploading, reboot the system, or whatever, and then the situation comes back to normal, right? But what's going to happen if a cryptographic algorithm, let's say there's a new research about it, but if a Sputnik satellite is up in the space like 1 year ago, if there's a vulnerability, do you have any protection defense mechanism? Is the first part of my question. And the second part about the keys. The keys where you have a confidential communication. What if the keys are compromised? Do you have a backup keys? What if backup keys have been compromised also? It's my first question. And my second question is about autonomous behavior. Let's say we have a satellite. It's only orbital cluster. But if one of the satellites have lost communication with the flight control center, and it has some autonomous like patterns or a mission embedded into it, like behaviors, not the mechanism of security, like recovery, but behavior. Like, what if you will not be able to restore calm communication? Let's start with the last one. Yes, we have it. The satellite is the maximally autonomous system and has some algorithm for cases like that. If there is no communication, the satellite should be able to live as long as possible. It keeps the energy, rotating towards the sun with the batteries and panels. It does everything to survive.
Sometimes it happens that communication restores few years. For example, there was shutdown, and in few years, satellite came back to life. It's alive and it's okay. As for the keys, there was a question, cryptography. This is something that can kill a satellite, because if you didn't do the analysis of faults in cryptography, then you have protected cryptography and communication channel, but the keys have got destroyed. That's it. It's alive, but you cannot get in touch with it because keys have been destroyed.
что там идет
So the first
резервирование.
thing, there is a backupping process by block by block, and there can be 3-4 blocks like that.
На разных частотах, разных технологий.
Different frequencies, different technologies, and this is all backed up and reserved. Also, inside, there's a full set of keys,
Собственно, схемы, когда аппарат
and there are schemes when machine does understand that
полетами не связался, и
center of managing the flights did not get connected to them.
менять ключи. Вот эти ключи.
And they can replace those keys. And these keys, well, there can be a lot of them, because the keys can get destroyed, the key can be compromised, but the compromising is the command to the spaceship, don't use this key anymore. So, something like that, I think I've replied to you. And from the point of view of unsafe algorithm, it's the same about modeling threats. For example, during the flight of the spaceship, the algorithm can get outdated. In this case, mitigating measure is a necessity of this algorithm to realize it in the software, and if you will realize it in the software, then when it's going to come, it will get connected. You can update the software, you can update algorithm and fix this vulnerability. Understand? Then I have another question about compromising. As an addition to the previous one, if the compromising threat of the sensitive information on the satellite object, and you have detected it, and the spacecraft comes into the state of being compromised, which of these modes are available? Is there a information destruction mode? What are the consequences? Well, these are very specific for the payload. We cannot talk about things like that. If the payload contains some sensitive data, of course, during modeling of threats and to compromising mode, this data has to be removed. That's true. Okay, thank you. Payload, antennas, telemetric, etc. We have a lot of questions. Please. So we'll limit ourselves with three questions. Who wanted to raise their hand? Okay, this, and you're going to be the third one. Hello, thank you very much for your presentation. It was very interesting. I have an answer about the payload. We've been testing approaches of dubbing and backing up those blocks, different blocks, so that the satellite will be in a workable condition as long as possible. And then receiving and transmitting equipment and the payload, yeah, it was like that because... Okay. So it was an answer, not a question. Yes, thank you very much for that. It was a transmitter. 20 and 40 megahertz transmitter for the amateur, and it was their payload. Okay, dear colleagues, let's go to our final question. Thank you very much for detailed presentation. It was very interesting to look at the structure of your system. And at the beginning of the presentation and about the payload, however, one of the theories is that radio frequency transmitters is ionizone ones, which allow to create different noises in ionosphere and study them. These noises are connected to the moment when we've been thinking about the research of anomalies in conducting what is being done when things like that are happening with those noises, which you cannot assume that. But you have some anomaly detectors which can react to these, and there will be some incident, whether it's the problem with the system or you have to continue. Thank you very much. Very interesting question. Very complicated question, because anomalies are such things which can happen in processes orthogonal to the functionality of the spacecraft. So in order to discover these anomalies, possibly it is necessary to have some additional equipment which is not available on the spacecraft. So it is very difficult. Usually we work through hypotheses. The hypothesis, checking the hypothesis, how is it possible to be checked by the software? If it has not been discovered in the format of threat modeling, then most likely it's going to be in fight. Some anomalies we've been discovering through a very extended hypothesis. Yes. Thank you very much, dear colleagues. Let's say thanks to our colleagues for the presentation. Andrei, if you allow me, please give the book for the best question. The first one who was asking, you had very interesting questions. Thank you very much.